欢迎一下哈。
Morning. Sorry for the late start, but computer troubles had to restart. So again, we're here to talk about parallel and GPU computing. Who here is already doing it? Anybody? GPU? Parallel? Who wants to do it? Yay, good. You're in the right room. I always like to ask a question. Who wants their Matlab code to go faster? If you're not raising your hand, I always have to ask, why are you here? Because that's the whole point of this session, is how to take what you're doing in Matlab, which is traditionally serial, one command after command, and how to make it run faster with a pool of workers. We generalize out workers so we don't have to talk about cores or GPUs or processors or computers. It's just a computational worker for us. Where those workers are, right now it doesn't matter. The whole fact is that there's a pool of workers, and how do we take advantage of it? Because as I said, it could be on our desktop, a GPU, a multi-core machine, a multi-processor machine. It could be a cluster behind the scenes on our network somewhere that we're trying to access. Again, it's just a pool of workers. We could be trying to work on our iPhone. Do you think Matlab runs on an iPhone? No, it actually doesn't. We do have an app, though, you can install on your iPhone to control your Matlab on your desktop from your iPhone. But the whole point is it's just a computational resource now in this chain, and we want to take advantage of what's out there in order to do our work. So parallel computing toolbox on the desktop, Matlab distributed computing server on that cluster that's somewhere else, or a grid, or whatever it is, a pool of workers, and then Matlab mobile for the iPhone that allows you to control your Matlab desktop. This isn't today's discussion. The other two are. So let's see what's new. So those that have been doing it, and I'm trying to find the right place to stand to not get feedback away. So those that have been doing it, let's see what's new, and let's take some examples of what's possible with it. So updates for the Parallel Computing Toolbox as of 11B, the latest release. Actually, some of these updates I'm showing here have occurred earlier, in earlier releases, but they are all available as 11B. Some of them are specific to the latest release, such as increasing the amount of local workers you can open up on your desktop to 12. That is available to you as of the latest release, 11B. Improved PAR4 SPMD features. We'll actually talk about some of these, but they've been improved. They go faster. Toolbox functions, more toolbox functions with built-in support. Don't even have to do any reprogramming. Job monitors for when you're dealing with grid. A lot of enhancements for distributed arrays when you're talking about large data that won't fit into the memory of your computer if you ever gotten an out-of-memory error. And deployment of local workers. Again, this is a 11B feature. You've created a simulation in Matlab. You're taking advantage of the multiple cores in your desktop to run it, to help it run faster. You want to share that with your coworkers who don't have Matlab, but you want them to have the same performance that you have. 11B allows you to take those local workers and deploy it out to your colleague through the Matlab compiler. For GPU, or graphical processing unit, we'll show a little introduction today. I know there's another session later today from NVIDIA to talk more about it. GPU accelerated built-in functions in Matlab. No reprogramming necessary, just a simple step of putting the data onto the GPU card, calling these functions. They will execute on the GPU card at increased performance for you. Random number generation, always valuable when doing simulations. We have that capability on the GPU. And as always, Matlab can execute GPU kernels, CUDA kernels programmed in the CUDA language directly from Matlab. It's a command you can just simply call. So that's some of the what's new. let's see some of this stuff in action. How can we actually get those performance increases? How do we actually take advantage of it? How do you get started using it is the thing. So we'll start off with a parallel computing toolbox, accelerating your code on your desktop. 12 local workers, no separate hardware required. You're just looking at your box here. We'll see how easy it is to scale up from your desktop to additional computing resources, whether it be a cluster or something else. We'll start off with talking about performance acceleration in terms of computational speed, but we'll also look at a little bit as working with large data. So again, start with large computer. And the focus of MATLAB's parallel computing solution hasn't just been making this available to you, but making it available to you in an easy-to-use form. You don't want to have to know all the specifics, all the low-level functions. You just want to get your answer as easy as possible. So that's why we have this process, this different levels of functionality available for you. We can start off with built-in support for toolboxes. Let's get my function to run faster by enabling a pool of workers, clicking an option, and letting my simulation run faster. And that's where we'll start, and then I'll show an example of the optimization toolbox. So here I have a script created in MATLAB that does a simulation for us. It's actually trying to optimize the coverage of an area with circles. Think of it as cell phone towers. How do we cover the largest possible area with the fewest possible cell phone towers? So we'll just let this run a little bit, step through it. And it's running. Right now it's actually calling an optimization function, but it's single-threaded. So it's going to take a certain amount of time to run. You can start to see the simulation, the result on how they're iterating, and how to optimize the coverage of that square with those circles, minimizing open space, minimizing overlap. And eventually we'll converge on an answer. It'll take a certain amount of time. Looks like we converged, so we'll just go ahead and so now it's actually going ahead. So we ran it for so many iterations. In this case, 37. And it took a certain amount of time, about 59 seconds, about a minute. Now what's happening is the code is actually opening up a pool of MATLAB workers. I have a dual core processor on my laptop. How can I actually take advantage of both cores? Because for that 1 minute that it was executing, it was actually only using one. Now in this case, it opened up a pool at 8, which doesn't make much sense, but it doesn't matter. We have now things running on both cores simultaneously. Some of them are sharing. And what hopefully you're noticing is that the iterations are occurring quicker. So 59 seconds. Go back to the, let me just make this bigger. 59 seconds when we did it one way, about half of that the second time using both cores in my processor. Want to know what those changes were? Well, we were running an optimization function, one that can take advantage of the parallel computing toolbox. So all we have to do it's already hidden in there. And we just call it the Optim tool. So it's a graphical interface for setting up optimization problems. You can pick your solver, your algorithm, and then if that algorithm is programmed in such a way, has been added by the MathWorks, we have an option available to you called use parallel. If you're using the functional call for this solver, this option will be there. Use parallel always. In this case, evaluate parallel. You simply check that box, which indicates to MathWorks, the optimization solver in this case, if there is a pool of workers available, please take advantage of them. Please let my stuff run faster. Who doesn't want their stuff to run faster, right? And it's easy as clicking a box, adding an option, an optional parameter statement in your call to that function, and then adding this one comment somewhere. Matlab pool, just make it easier. Matlab pool open, and then the number of workers. So in my case, I would like 2. Check that box, run your code. It's actually now going to take advantage of that pool of workers that's open. Very simple and easy to do. What other toolboxes have had these type of additions made to them? Well, here's just a sample. Optimization, global optimization, statistics. Not all functions have been reprogrammed to take advantage of parallel computing if it exists, but there have been some. Statistics, design optimization, bioinformatics, model-based calibration toolbox, and many more to come in the future. Parallel computing is not going away. Computers aren't going back to single core anytime soon. The MathWorks is investing heavily on trying to take advantage of the hardware that you're buying today through parallel computing. And we want to make our functions and the toolboxes that are using to solve your problem use that hardware as well, with you just using the calls. So the next step up is actually starting to create your own parallel computing programs. But again, we want to make it easy for you. We don't want you to have to worry about a large amount of new commands to worry about and think about to handle the communication and the splitting up of your program amongst the different workers. So we've come up with constructs. We call them simple level constructs. One I'll be demonstrating is called the par4. Who's here has used the par4 command before? How easy is it to use? Easy? Yeah. How useful is it? Very useful. Anytime you have a for loop that has independent iterations, you can simply make it a par4 and watch it go faster. And the whole idea of this par4, of any parallel computing actually, is to exchange computational time, doing things in serial. So in here I have 4 tasks. I can do those in serial, one after another. Or I can try to do them in parallel. I want to do them simultaneously at the same time. I'm exchanging time for computer resources. Computer resources are pretty inexpensive. So that's what we're looking for. And the examples where the par4 in this type of situation happen frequently in engineering, parameter sweeps. You have some type of model simulation of some system. It takes inputs. You want to know how the response, the output varies as that input varies as well. Each iteration, each set of input parameters is independent. But you're sweeping through a wide array of them. The other, Monte Carlo simulation, it's the same kind of idea, but you're trying to understand the randomness, the distribution. My inputs aren't systematic at this point. They are random. And how does that randomness impact, again, my response? Independent simulation. So we can look at trying to do a parameter sweep of a solution to an ODE problem, ordinary differential equation problem. So we'll actually go ahead and look at this. So here's my system of ordinary differential equations. So it was a second order differential equation that we were trying to solve. N times the second derivative of x plus b times the first derivative of x plus k times x equals 0. We substitute in for it, derive an order, two first-order differential equations shown here. And then this is what we're actually going to use the numeric solvers to solve. So that's our system. And now we're going to try to go ahead and solve it, but just not for one parameter. We're going to set up our solution to look at a combination of different values for the coefficients b and k. Not just one, but two. So again, we're sweeping through a bunch of parameters. We can do it as a for loop, just a regular for loop. In each for loop, pick out a set of parameters. Give me a value for b, give me a value for k. I already have n. Solve my system of equations. Solve it. Move on to the next one. In this case, we're only going to store the peak value just so we get a sense. We look at the time. And we're letting this go ahead now and evaluate. So it's computing in serial. Again, this is that standard type of engineering study, parameter sweep. Very similar to Monte Carlo. So it took 16 seconds. Now in the next one, since I already have that pool of Matlab workers open, I won't open it again. How do I know it's open? Tells me right there. I have 2 workers open. So within this loop section now, this is the exact same thing as that for loop we saw earlier, with one change. For became par for. We simply run it, because we already have that pool of workers open. Seconds, 8 seconds, we cut the time in half. Imagine if we had a bigger, more powerful computer. 16 seconds could become 4 seconds, 2 seconds. Well, we would start to hit the limits of actually communication between the workers by the time you get to that sort of small problem. 16 seconds really isn't a very large problem. But what if it was 16 hours? Larger computer can start to make a huge impact at that point. And that the communication between each worker, giving it a job to do and bringing that data back would then be a very small fraction. And you could start to see powerful things. 16 becoming 8 hours, becoming 4 hours, becoming 2 hours, becoming an hour. To get an idea, we got the solution. That's our sweep. We got it both ways. If we wanted to look at a speed up We're looking at exactly 2, a factor of 2. Will you always get exactly a linear factor? No. There's communication between when you're distributing this job. That's what I was talking about earlier. If it's a very small problem, breaking it up into lots of small parts eventually doesn't help. But it's a very large problem, and then communication is very small. Big, big gains. And then we also allow full control of parallelization, what we call jobs and tasks. The par 4, that entire loop is a job. Each iteration in there is a task. What if what you need to do in parallel, you want to do quicker, cannot be structured as a for loop? You're not out of luck. You just have to go to jobs and tasks to create your own parallel application. One other change from going to jobs and tasks is switching from running my parallel application interactively like we have been doing on my desktop. I go ahead and press go, it runs, to actually scheduling the job. My Matlab code, when I run it on my desktop, doesn't actually execute the simulation. It just simply creates the jobs and tasks, and then I must submit the job to whatever resource I want, and then it will actually execute, scheduled in that sense. For an example here, in this case, what if we wanted to solve that same system of equations, but we didn't want to sweep through parameters, we wanted to sweep through different solvers? It's not a for loop anymore. But I have these things I want to do. I have solver 1, 2, and 3. Bigger. Analytic. An analytic solver. A solver using ODE 2, 3. ODE 4, 5. And then ODE 1, 5S. So one stiff method. How do I actually create this? It's not a for loop. It's these different solvers. This is normally how you would do it. In serial, call one solver, let it solve, store the results. Let it finish, do the next one. But again, I want to do this in parallel. So this is how I change. I create a job on line 38. Schedule just means what resource I want to send this to eventually. It could be local, your local machine, it could be something else. I'm setting up some file dependencies. Wherever I send this job, it's going to need a copy of the custom functions that I've created to do the solution. Just like any Matlab function, if you run it, you need a copy of it. Those workers will need a copy. And that's what file dependencies is doing for me. Create jobs, create tasks, is just doing that. Create a task that will be this execution. Put it in job, so create a task, store it in job. The task is to execute that function. I expect one output. I want one output. Here are my inputs. That's it. A mechanical translation of the line that you saw before. Instead of running, instead of output equals function with input, in this case it's create task. Here's the task to be done, but with the same number. And when you have it all set, line 50, submit the job, let it go run. That's when the task will actually start to be executed. And then you can get your results. So again, it allows you to customize your own program. Yes? Yes?
you sketch the task 1 and the result, then you can see the task 2 can follow. Some interconnection between. See what I mean?
Yes. So the question is about dependencies. What if my tasks, what if my things I'm trying to do have some type of dependencies? Well, what I've shown so far is dependent on no dependencies, being independent tasks. The great thing about the parallel computing is you can start to customize in that respect one set of stuff that can be run independently. Underneath it, another set of stuff that depends on the answers from the above. So you're introducing and mixing serial programming with parallel programming. So within MATLAB, you can use both within the one script. And that's actually what I've started to show. One script, we had a for loop, we also had a par for. It could happen that you run something here, then you run something in parallel because it needs the answers from before, and then you feed it down into some other task. And it can all be done in one single script.
And then the complexity, another aspect is that when I try to call some functions, just create the function and try to take some of the polynomials. So it's not so bad that I have to call it this again.
So can you integrate in functions created by someone else, maybe in C?
Because the library I even want to take maybe some synology, but they have to be so but it's not at the same time.
Yeah, so the question is about integrating in libraries that you've obtained from other ways, whether it be a colleague, a third-party vendor. And the answer is yes, you can actually call and have your functions in parallel MATLAB calling out to these third-party libraries. You would want to have to do that file dependency or make sure that those libraries exist where the workers are so that they actually can execute. But you can actually have them call. The other thing that you have to check is the licensing. If it's something you or a colleague created, you don't have to worry about it. But if it's a third-party commercial software that you bought, you have to check to make sure that their license allows you to run multiple instances. But the MathWorks solution for parallel computing will allow you to call out for multiple instances. You just have to watch. So, talking about that. Kind of running short on time, so I'm just going to highlight the capability. I'm using MATLAB for large data. This is that out-of-memory error. You can interactively open up a pool of MATLAB labs and start to create distributed arrays. An array that is so large you would have gotten an out-of-memory error on your computer now can be stored on two computers. But as far as you're concerned, it's array A, just as variable A, just as if it was on one computer. We have a programming construct very similar to the par 4 that allows you to do this programmatically within your script called the single program multiple data construct, SPMD block. Within this, there's one program, but it will run on different labs, different workers, and can have different data, or even stitch data together across multiple workers. So it's a programmatic way of dealing with large data. And again, within this block is parallel computing. Anything above and below this block is serial computing, so you can mix and match serial, parallel, par 4s, whatever, within one script and start to deal with conditionalities. I wanted to kind of go through that a little bit faster, so we had a couple more minutes for GPU computing, because I do want to help start introduce this for you. And the whole idea of GPU computing is not to actually have my calculations run on my CPU, my central processing unit, my Intel processor, or my AMD processor, but it's to have it run on my graphics processing unit. Why do that? Well, graphic processing units are basically massively parallel processors. So instead of doing 4 threads, I can do hundreds of threads. The Parallel Computing Toolbox is supporting NVIDIA CUDA, so the Tesla cards, because the NVIDIA people are here and are giving a session later. Just like before, we can actually have a lot of different ways to interact, but it's CUDA. Just to give you some terminology, is the computing technology from NVIDIA, so their branding. The device is the actual card. The host is the CPU system memory. Traditionally what you think of as your desktop computer. And the kernel is code that's written specifically to execute on the GPU, so it's the CUDA implementation. Just like Parallel Compute Toolbox, we have this ease of use versus flexibility requirement. GPUs, you can create GPU arrays very simply in Matlab, and then if the function that you're trying to call, Matlab function, supports GPU arrays, it will execute on the GPU for you, no programming, no additional work necessary. And you can take advantage of that processing. You can create custom functions, and you can actually create your own custom kernel in CUDA environment and bring that in as a Matlab function. You call a Matlab function, it's your own custom function. It's executing the CUDA kernel on the GPU, but you're just in Matlab as a regular function. So to give you an example, I actually have a laptop here that does not have a GPU, and I don't have internet access at the moment. So I can't actually show you things, but I'll demonstrate what type of changes are necessary and what type of things are possible. So in this case, if we were to try to run a solution to a second-order wave equation with different grid sizes on the CPU versus the GPU. Well, I can show you a video of that. Here's the solution. It's accelerated time, but you can see the execution time down here. It's a little small, but in a second we'll see it. So we've seen the solution. It's the time scale is proportional. So whatever acceleration factor I use on this will be the same one that I will use for the GPU solution. So the relative effects are the same. It took 13,000 seconds to run on the CPU. The same thing on the GPU. 1,800 seconds. So that was a speed up factor of, what's said up there, a very large speed up factor for you by just changing where I'm running this. Was this simple to do? Well, this actually ran a custom kernel on the GPU, so we had to create the kernel itself. But you can start to get a sense of the types of accelerations that are possible. Is this possible for all problems? No. But for some problems, like this, where it becomes very close to the type of mathematics that the graphical processing unit was designed to do, you can get very, very high accelerations. Now for the ease of use. If you want a GPU without having to create anything, here's a traditional Matlab way of solving a problem, say a wave equation. Simpler one. Initialize, start my steps, in a loop, let it run. Now I want this not to run on my central processing. I want it to run on my GPU, my Tesla card by NVIDIA. I simply have to tell first Matlab to put that data onto my GPU. And that's what the GPU array is doing. It is transferring the data from my system memory to my GPU memory. Once it's there, those functions, real, FFT, IFFT, can support GPU arrays. They will run and execute the calculations on the GPU for me, and all I have to do to get my data back is simply gather it off of the GPU card and put it into my system memory. So if what you're trying to do has functions that are supported directly for GPUs, it's that simple. If not, you can create your own custom CUDA kernel. We'll be around more for questions, and as I said, NVIDIA is having a session later today. To give you an idea of the speed ups possible, 7.5 down here. But also notice no speed up. The speed up you can get is dependent upon the size of the problem, the amount of communication, transfer of data between the CPU and the GPU, and also the mathematics themselves. So we offer this as just a suggestion of what's possible, but we also offer it with the warning your results may vary and will be very particular to your particular situation. But you still have regular parallel computing on the CPU if GPUs aren't advantageous. So the choice is really up to you. We are offering a selection for you. And again, for GPUs, a couple good notes to look at. For GPU, you want massively parallel computations because it is a massively parallel processor. And you want it computationally intensive. Anytime you're exchanging data between the two systems, you're slowing yourself down. Just suggestions. Support, again, requires NVIDIA compute capability. Why do we choose this? Supports doubles, guarantees IEEE compliance, so your numbers will work, the results are the same. An example of invoking a CUDA kernel. So mykernel.ptx, mykernel.cu, that's the CUDA kernel, the script made in CUDA. And the rest are what's just needed in order to use it in Matlab. Parallel.gpu.CUDA kernel, give it that. You get this thing called, an object called, in this case we're calling it kernel, that contains that functionality now. Simply evaluate kernel with the A and B, and that set of calculations is running on the GPU, but it's a Matlab function call. It's not a large process. You can also scale up to multiple GPUs. And just to review, one of the major new features with parallel computing as of 2011B is the ability to deploy those calculations on local workers and GPU workers out to other people through the Matlab compiler. So if they don't have a Matlab license, you can share your work and let them attain the same type of performance increases you have already had. So in summary, parallel computing is all about getting your answers faster with hardware resources you probably already have. If you want it even faster, you can do GPU clusters and CPU clusters. Those clusters will be running a complementary product called Matlab, which should be computing server. On your desktop, you're just using Parallel Computing Toolbox. And you can get started scaling up and working with additional resources on your desktop. And then if you need faster, go to those things. I'd like to thank you for attending this session. I think it's lunchtime, is it not?
借助大家掌声，再谢谢他。